Well, in the next, we continue discussing the risk bound. Have a short review of what we have arrived now. We have considered to evaluate a single hypothesis on a training data set, where then there is some probability that the evaluation is not accurate with respect to the out of sample error. That risk is manageable by increasing the number of data set, the number of data samples in the set. However, when we are going to consider the general hypothesis of selecting one, a general risk of selecting one hypothesis from a hypothesis family, if we take the naive approach to accumulate all the hypotheses from the members of the family, because the family goes to going to have infinitely many hypothesis members, then we are lose control of the general risk. Then we considered to use the relationship between evaluating a hypothesis using one dataset and consider the risk that evaluation is wrong, and the risk of evaluating one hypothesis on two independently drawn datasets, and the risk of these two evaluations differs from each other very much. Those two events are linked with each other. So we establish the relationship, and now we will be able to limit the risk of learning using the risk of the learned hypothesis evaluated on two independently drawn datasets. And in the next, we are going to use this conclusion and see how we can use this formulation of the risk to limit the overall risk of learning. Before we consider the general risk of the learned hypothesis evaluated on two datasets, and then we end up with a large difference. As before, we first consider such a risk for an individual hypothesis. Actually, we have another Hofstad's inequality, just as when we are comparing the E in and E out for this kind of difference. But before that, let us consider a few facts about the evaluation. So we are going to consider the different measuring the hypothesis performance on two independently drawn data sets, and we are going to consider the risk of the difference is exceeding some preset threshold, and the threshold was derived from the threshold we were going to establish for our previous risk bound. The facts we are going to consider are for given the two subsets, two data sets, each of n points, the evaluation results are two random binary n arrays. Each of the array contains n values, and all of the values are either zeros or ones. Let us say we use 1 to represent that the hypothesis to be tested makes an error at a particular data sample in the array, and 0 means it is correct. So in this formulation, the two in-sample errors evaluated on the two data sets, let us call them A in and A in prime. They are mean values. They are just mean values of the two arrays. And using this consideration, using this formulation, we can consider an equivalent construction of the same formulation. Let us think the problem in this way. We first take 2n samples and evaluate the hypothesis to get the 2n array, binary array of zeros and ones, one representing the errors as before. And after have evaluating the the hypothesis on the 2n data sets, we then randomly draw n samples from the 2n array without replacement. So this is a tautology-like consideration, but this is necessary when we try to apply another theory about the difference between them. So this is equivalent as we independently draw 2n samples and evaluate our hypothesis on the two training data sets. So let us consider the n samples we randomly drawn from the 2n samples to be the original data set, and the evaluation and the mean value of the evaluation of the hypothesis there give us E in. And then we are left with another n samples. Let's consider those n samples. The new data set, and the mean value of the evaluation the mean value of that array to be E in prime. In this setting, we have a new inequality, which is given by this equation. It is to say, when there are 2n zeros and ones for such an array, if we randomly draw n samples from these zeros or ones and consider the mean value of the randomly drawn array of n samples, take the mean value of it. So consider this term linking to A in, and let mu to represent the overall mean value of the n samples. Then the mean value of the drawn n samples, mu is the mean value of the 2n samples. So the mean value of the n samples differs from the general mean value of the 2n samples by some amount. If this amount exceeds some threshold t, let us use a different letter for that, then this event happens with a probability less than this bound. It looks very similar to the original Hofstad's inequality, but this refers to taking a subset, half of the population, from a given data set, given 0 and 1 set. The advantage of this, it eliminates the unknown out of sample error in the inequality, in the calculation, and therefore it is computable. So let us try to establish the link between this given inequality and the target, what we are interested in, the target event. So because we have established that A in is just this mean value of the sampled sampled n the sampled the joint samples from the 2n samples, and mu is the general mean. So we have p En minus mu. If this is larger than t, then it is the chance of this is below to this bound, to t squared and n. And notice that because E in prime is just the mean value of what have been left by drawing z1 to zn without loss of generality. We can just say we draw z1 and zn. That does not matter from 2n samples. So using this sample, we can see En is the mean value of z n plus 1 to z to n. And then we have the relationship En plus En prime divided by 2 is just mu. So we can substitute into the new inequality here. So we have P A N. Let us concentrate on the event itself. A N mu. The difference is A N subtracts A N prime divided by 2, which is half of A N and A N prime. So we have the absolute value of it. Well, this is closely linked to the event what we are interested in. We are interested in the event A n prime differs by something exceeding half of epsilon, and epsilon is the original tolerance we want to establish between E in and E out. Well, then we can consider when A n u, this means prime, and move this half here, and then we establish this link to have the red inequality to describe the event in this red box. We just need to let t equals a quarter of the epsilon, and then we can substitute this t value into the bound here, and we arrive what we need. So we then arrive to P A n and A n prime's difference greater than half of epsilon. That bound is bounded by, the chance of this is bounded by 2e2, and this is epsilon over 16 and n, 2e minus epsilon squared over 8 times n. So that is what we arrive. Okay, using the link, we got what we have or what we want for the bound of evaluating the bound of the chance that the evaluation of a hypothesis on two independently joined data sets is exceeding some threshold to half of epsilon. But of course, we need to remind ourselves this is the risk for a single hypothesis. Then how about to consider this risk for a hypothesis that has been selected by some algorithm from hypothesis family? If we continue following our intuitive way to do that, we will accumulating this risk for every individual member of the hypothesis family. And then we immediately arrive with this summation. This is constant in the summation, so this becomes the number of hypotheses in the family times the bound, the risk bound we have established for the individual hypothesis, which you might think is useless, just as for the same reason we cannot use this derivation to use we cannot follow the same derivation to use the original Hofstad's inequality. However, because now we are considering evaluating the hypothesis on 2n samples, we are no longer worrying about the entire data distribution, the E out. The E out is now out of equation. By removing E out from our table, we will be able to find a clever way to count the number of hypotheses. Well, in this case, we'd better to be specific to count the varieties for the members in the hypothesis family can achieve using this limited number of training samples. Well, there might be infinitely many hypotheses, but we are now remove the infinity stage of the data space for them. So those performers have to act themselves out on limited number of samples. In this way, we will be able to limit the variety of the ways they could achieve the risk, they could incur the risk. In the following part of this lecture, we will discuss ways of counting hypotheses, counting the implementation, the realization of the hypothesis members of the family in clever and limited and finite way.